Thank you, Gar.
Okay, thank you
Thank you
both.
all for coming. I'm amazed. I was told there would be 2 people.
Well, I wanted to prepare you for that. With COVID and everything, I thought it was good.
So, okay, well, we could go. We are here. This is somewhat experimental. Certainly the first time I've talked about most of this stuff. Excuse me for using the word stuff, because I use that word in connection with energy. Energy is the stuff of the universe. Okay. This is quite a lot about thermodynamics because, well, you'll see why, I think, I hope. From humans as playthings of the immortal gods to the humans as good gods playing with the planet. So you see a nice picture of how you might look at the sky and see something pretty weird up there, like a god. And the second one you see is as you all know, Michelangelo painted this picture. It's one of the more famous tourist attractions in the world. And it shows the creation of Adam, only Adam. Where's Eve? She got made out of his rib. And people did calculations. When did this happen? And the most popular number was 4,004 years before Christ. Calculated by an Irish bishop. Okay. Well, there were other important myths back then that we've mostly got rid of in this 500 years. The idea that there were 4 elements. Air, water, earth, and fire. This all came back from Greek times. They had 4 humors. Those were the liquids in the body. They were blood, phlegm, yellow bile, known as color, and black bile, melancholy. And of course, dualism vitalism was very popular back then. Elan vital, or life force, was thought to be something that differentiated living organisms from non-living. Pasteur was a vitalist. Well, there's some of the famous names of people connected with the early stages of science. Da Vinci is interesting because he was a scientist without knowing it. Descartes, Giordano Bruno, interesting man. One of the interesting arguments of the day, those days, was monism versus dualism. Monism is the belief that there is only one fundamental essence of the universe, and we now call it energy, and so on. I won't take more time. Here's a graph. History of the radius and the temperature of the universe. Look at it's very highly logarithmic with many, many, many powers of 10. But when you get down to the logarithm of the logarithm of the logarithm, enough times you see a set of curves like this. The rising curve is the radius of the universe. The declining curve can be interpreted really. Well, the rising curve would, I'm sorry, the declining curve is the temperature, many, many powers of 10. And the rising one can be considered to be something like the entropy. Structure of the sun, well, all the energy that we see use basically comes from the sun or came from it, with a small little bit of exceptions, the exceptions being, as you'll see in a minute, atoms of atomic number greater than 26. I'll explain that in a minute. Fusion is taking place in the center of the sun. The fusion involves, initially in the early stages, it would be simple hydrogen atoms fusing with each other, making heavy hydrogen, and then by several stages you get up to helium, and after that you go all the way to iron, but not further, unless you're in the middle of a never mind. The carbon nitrogen cycle is illustrated here. That comes after the fusion that gives us helium. And then after that, we'll go all the way to the periodic table because, and this is very important for the Earth itself, because even though the elements heavier than iron are tiny, tiny, tiny fraction of the total, we would not be able to do much without them. And most of our technology depends a lot on those heavier elements. And they came out of a supernova. That's the word I was struggling with for a moment. They all come, those heavy elements all come from the explosion of a heavy star, a large star, much bigger than our sun. So it was a previous supernova that gave us the heavy elements, of which this Earth is well endowed comparatively. Okay, and as you see, the next slide is that's the slide showing the abundances of the various elements, and you see a big peak there. This is highly logarithmic again, many powers of 10. And the peak is iron, and that's because at the end of the sequence that you get of fusions that would occur that would release energy. And after that, you have to put energy in to get heavier elements. But that's what happens in a supernova. The next slide, skipping from cosmology to biology. This slide called the Kelvin cycle. I guess everybody here, because you're all many of you are biologists, you all know what that is. Yes. Anybody who doesn't? It's the cycle that produces photosynthesis, or that is photosynthesis. It produces glucose, and it combines carbon dioxide and water vapor. But that combination has to be energized by a photon, or several photons. And it's actually rather complicated. And in the course of that cycle, a protein called, what is it called? Chlorophyll is called. Chlorophyll is the protein that is produced on the surface of the Earth in the largest quantity by far. And but we haven't learned to eat it. Kelvin cycle, named for its discoverer, Melvin Kelvin, I think it was 1937, is the only known mechanism to explain photosynthesis. The only one, the only known mechanism. The process where energy from the incoming photons, red and blue light, enable carbon dioxide and water to combine, yielding glucose. And it all takes place inside the chlorophyll protein. Okay, move on. The next one, this is quite interesting for a reason that I will explain. Well, there it is actually, coming up. This is the so-called citric acid or Krebs cycle. Mr. Krebs was, I did say Kelvin was Melvin Kelvin. Okay, this Krebs was Hans Arthur Krebs. I guess he had a PhD student at William Johnson. He didn't get a Nobel Prize. And then they're all based on earlier discoveries by Emeritus and Ecology. This shows how glucose is oxidized in the organism to produce energy that can be used for anything that you need energy for, but the one that really consumes most of that energy is motion. So this is what made it possible for the invention of this cycle made it possible for our biological evolution to produce animals. So the whole cycle of attack, escape, all that stuff came out of this. But there's more that came out of this. The next slide is the carbon-oxygen cycle. And I guess probably all you biologists know know the reason for this, but I'll say it anyway. If you had only photosynthesis organisms, there would have been no evolution, because the photosynthesizers would have died off because their byproduct, their waste product, which is oxygen, happens to be toxic. And so now we needed some clever compromise had to be created in evolution to make it possible to have both photosynthesis and also some way to use up that oxygen to keep it from killing everything. And that's what this is. It's the carbon cycle, so-called. And it's that balance that enabled the invention of animals, really. And without animals, we wouldn't be here either. This is a scheme for such cycles, because the carbon oxygen cycle isn't the only one. It turns out that necessity for recycling is not just unusual, it's normal. Because normally, organic material at the end of its life tends to become unavailable some way or another, often very sinks to the bottom of the sea, or it's insoluble. So it takes a form that's extremely stable and very hard to recycle. So cycles are needed to get those, I'll call them nutrients, back into the system. And after carbon and oxygen, of course, we have nitrogen, and we have phosphorus, and we have sulfur, all of those three, and there may be more. Well, of course, the metals in a way are being recycled also, but mostly by humans. And it's interesting, very interesting, that I'll come to a explain why this is so interesting. I think it comes very soon. Okay, well, here's the nitrogen cycle on the left. That's it. Yes, that's it. I won't take time to go into the details of it. Just look it up anywhere anyway. Sulfur cycle, another one. And there is a phosphorus cycle. I don't think we have it here. And here are cycles linked to cycles. And that looks like maybe how life itself got started. Cycles linked to other cycles. This one is an artificial one. It's a schematic model of something called a kiloton. It's a self-replicated chemical system. All organisms are self-replicated, self-energized, self-replicated chemical systems. And the next slide is something you've all seen many times. It's the double helix of DNA. And I've forgotten how many thousand molecules there are in this. It's a very, very large polymer. But all of it is made up of 4 nuclides, so-called. The ones that are the crossbars of the ladder, of this helical ladder. There are 4 of them. They're called cytosine, guanine, adenosine, and uracil. Start to read. And all of them contain phosphorus. Phosphorus is quite a rare element, and phosphorus doesn't get recycled naturally as much or not as easily as the other nutrients. This is a very curious and very interesting phenomenon. And I've been asking around, maybe some of you have an answer. Is there any natural phosphorus recycling organism in the ocean? Maybe there is, because otherwise it's awfully hard to explain. Although phosphate rock, which we mine and then refine to make phosphate fertilizers, all of it, according to the experts in the Geological Survey and so on, that's all a biological element. So how did it get into the biological system in the first place? Well, that's an interesting question. Move on. The next one, by the way, I couldn't get it labeled properly. It's the menstrual cycle of ovulation. Very complicated, very essential. And it's very, I say complicated, I think I read that it had about, how many, 20 some hormones from about 10 different organs. 6 of them are glands and the others are non-glands. Kidneys, for example. Anyway, point being, it's a very complex system, and all of these 20 some losing words, 26 hormones have to be coordinated. Very system. And yet, mostly it works. It's amazing. It really is amazing. Now, that has all of these things that I've said so far have enabled biological evolution to occur. And, evolution, as you know, has been occurring for a long time. And it has produced a huge number of different species. Many, probably by far most of them have already disappeared. Have been replaced by other ones that are more fit according to Darwin's ideas. But we now have an extremely wide variety of organisms, very complex, so on. Biodiversity is the picture here. And on the next one, I don't know how famous Buzz Holly is. I thought he has his own cycle that he calls it. It's a cycle of, where would it start? Creative destruction, bottom right corner, followed by exploitation. Well, I don't know that cycle. It's a little funny. Anyway, 4 stages: renewable, conservation, exploitation. No. What is the order? Anyway, there's 4
The
stages.
order starts with exploitation 1, 2.
Oh, yes. Okay. Oh, yes. It's hardly visible. Yes. Exploitation of an ecosystem by other species, for example, by us, followed by conservation, followed by creative destruction, followed by, oh, I see, that's this certain, followed by a renewal stage. And so I guess there's need to say more there. Here you've seen this diagram probably a lot. It's the diagram most often used to explain climate change. And it is true, it is a fact that the yellow input, yellow
Radiation.
yes, the yellow radiation losing it. Coming in has been exceeding in energy content the purple going out. So incoming radiation, which is higher frequency, infrared radiation, purple, lower frequency, but the yellow input has been exceeding the purple output for many, many years. And for much of that time, that higher energy input has simply resulted in heating of warming of the ocean itself. The deep ocean is so big that you notice this change for quite a while. And it wasn't noticed in terms of the temperature of the ocean. Still, it's hard to see. But since then, we've had consequences with the atmosphere where the amount of energy involved is much smaller. It doesn't have so much, anywhere near so much storage capacity. And that is basically what's driving climate change. Now, there are several all right, let's move on. This next one is the hydrological cycle. It's all about evaporation, condensation, precipitation in various forms, water, ordinary water as rain or as snow or as ice. And those cycles are, to a large extent, driven by planetary motion. Lunar orbits around the sun, around the Earth, or the planetary orbits around the sun. And those orbits also change over thousands of years, but I won't go into that. And then there's an atmospheric counterpart to that diagram showing jet streams and trade winds, which are also driven by this excess of energy coming in. And enough said there. So now I'm coming to people and the idea of energy, and there's no really systematic way to talk about it, but some interesting names. Ben Franklin gets on the list because he's, there's a book that you recommended, Ayres' book, where it says that he something, the gods, like, he what?
Something about lightning coming from the gods was the belief.
He
up
proved
until
it,
that
yes,
point, and he proved that it wasn't.
Yeah, he proved that it was a spark.
Spark.
Okay, wrong phrase, that's too bad. Benjamin Thompson, guy who was one of the American Revolution who fought for the English side. Went over there afterwards, made a living drilling cannons for the king of Bavaria, and came up with measurements for the first time of how much heat and how much mechanical energy it took. Relationship between temperature and mechanical energy from the boring machines. That was all done in more detail later, but I think he deserves the recognition. I was 1798 when that recognition first was quantified. The basic measures of thermodynamics, temperature, heat capacity, and that sort of thing were already worked out even before that, mainly by Joseph Black, professor, amazing number of Scots. He was a professor in Scotland, friend of Black. Okay, Sadi Carnot is the one that gets most of the credit for creating or inventing thermodynamics. And he did come up with this. I think we have it here. Okay. That's him.
No.
That's not here. Okay.
Okay.
Well, he came up with the thing called the Carnot cycle, which is very famous. And it just shows how mechanical energy and heat can be, well, how heat can be converted to mechanical energy in a cyclic way. And he found the most efficient cycle and so on. And it turns out you can do it the other way around, and you can put mechanical energy, but you don't get more heat, you get refrigeration that way. That's another story. Robert Ayres is one Meyer, actually, the doctor. But he came up with the idea, specific idea of conservation of energy. They called it craft back then. And then there's Rudolf Clausius, this is 1850 already, who finally did it all, and it was in a coherent set of equations, and came up with the idea of this measure thing called entropy. That was from Clausius. And a few more people I'll mention now, I guess. I said we'll put them in this place. Albert Einstein, you've all heard of. Albert Einstein was first to explicitly wrote an equation that says that mass and energy are equivalent. E equals mc squared, by far the most famous of all equations. Interesting. But that interchangeability was what prompted, when it was realized by physicists, it was when they started looking for ways of utilizing that. And we came up with nuclear weapons. I'll stop on that part. Then we have 1942, well, 44, Erwin Schrödinger, a very famous physicist, one of the most famous, who was also Jewish, and he was a refugee from Nazi Germany. He went to Dublin in Ireland for the war, and he wrote, did some public lectures there, and it ended up as a book called What is Life? And that book contained the first really clear exposition of an idea that's just now being understood, being grasped, that there are two forces or two tendencies involved in life. One of them is information passed from generation to generation, order to order. Created, order passed on, order preserved, and that's what DNA is. It's the order storage unit for the information by which all the proteins in our bodies and all the other species in the world are stored and passed on. That's order from order. And then there's another tendency which is much less well understood, and that's order from disorder. And that's the reason I use this idea of order as the title of this talk. Of the economic system. Okay, I'll say it all at once here. The economic system is a living organism. It is a living organism. It's driven just as other living, it depends upon, as all other living organisms, energy from the sun and so on, directly and indirectly. And that energy input is order from disorder. I can talk about it in different ways for a long time, but I think we'll just move quickly. I'm running out of time. Here's economics as science, as a closed system, and this is verging on a mistake because, of course, it isn't a closed system. But back in the physiocrats in France, back in the 18th century, saw it as a closed system. Every economist since then, virtually, almost everyone, until very modern times, has seen the economic system as a closed system of production, consumption, money flowing back and forth, energy going around and around. But I'll have more to say about that part. Okay, so let me just, yeah. Okay, you see how this is kind of stopping point. Yes, we could go out for coffee here, but no. You've seen how the universe has evolved from the Big Bang, assuming it did happen, and there's arguments about that. While the universe expanded and cooled. I showed that diagram of the expansion and the cooling. From a thermodynamic perspective, all the wonderful complexity of life and of civilization, which is part of life, has been driven by dissipating fluxes of energy from the sun, mainly. We call it exergy because it's the useful part. Exergy is the energy that can do work. The other part is called energy, which doesn't do work. As the exergy is dissipated, some say destroyed, both the entropy of the universe and its complexity increase. So that rising curve showing the radius going up, which you could interpret also as the entropy. You can also interpret that as the complexity in the sense I'm talking about already. So we have both order, both disorder from order and order from disorder. And here's just a few people: Adam Smith, Thomas Malthus. Adam Smith is known for a lot of reasons. I won't go into much of it. Thomas Malthus is known mainly for one thing, and I guess you all know that. He was worried about overpopulation because he thought that the resource base of the world was fairly small and the potential for population growth was unlimited. And the people are still talking about that one. Jeremy Bentham was the first man who talked in terms of utility and utilitarianism and hedonics, which is interesting, but I won't go much into that either. Ricardo, who perhaps was the first to put it really as, to think really of economics as science. I don't know if that's true. You could say so. But he talked about comparative advantage and trade, and that was very important in some way. I'm going to skip through all of this. Father economics, Marx. Okay, let's come to this. Economics is notorious for cycles. The simplest way of thinking of it is the boom-bust cycle, but it's the business cycle. And it's been bugging people for 200 years. How is it that we have these cycles of prosperity, followed by a crash, followed by a recovery, and another period of prosperity? And why does this happen at a fairly regular rate? And it's never been really well explained. There's lots and lots of hypotheses, lots of discussion, thousands of papers and hundreds of books. But here's four major cycles that have been postulated by economists. There's a 3 to 5 year inventory cycle, so-called, identified by an economist named Joseph Kitchen, 23. There's a 7 to 11 year fixed investment cycle identified by Clement Juglar, and that was way back in 1862. And then there's a 15 to 25 year cycle. These are never very precise, of course. infrastructural investment cycle identified by Simon Kuznets, and finally, a very long cycle, which is still very questionable, 40 to 60 year cycle called, were named by author Nikolai Kondratiev. And here's the Kondratiev cycle. And it is sort of visible. People have been talking about it for a long time. Me too. I've been involved a little bit in that. And then I'm going to move on to the circular economy. This is a popular subject right now. And it's interesting for physicists because, of course, it's impossible. Violates the law, conservation, etc. But of course, we can think of it as a hope and objective to come as close as possible to the recycling economy. And as long as the sun is shining, at least we have the energy needed for the recycling processes that have to be, and in some cases, yet to be invented, and some will be. So then, moving on a little bit, there's a dichotomy. We're up against a split. On one side, that's my side. Energy is the substance and the essence of the universe. That's monism, by the way, going back to early philosophy. We capture and degrade fluxes of energy and increase entropy while so doing. Energy from nature, from the sun, almost all of it, to drive cycles far from thermodynamic equilibrium and also economic equilibrium. So the economy is, in fact, a living organism. That's why it's possible, because as an economist, I'm not an economist, chemist really, named Prigogine, showed after Schrodinger talked about order from order, order from disorder. Prigogine showed how this fits into ordinary thermodynamic language equations and so forth. He showed that it's possible to explain life in thermodynamic terms. Now, mainstream economists to this day, I think unlike Mr. Vandenberg over here, but most mainstream economists divide the economy in sectors that do not use energy from nature, but only as embodied indirectly in other products or services. This exaggerates the productivity of human labor, the people who are employed, create value added, so-called, in the sectors, while greatly underestimating the productivity of energy itself. So basically what I'm talking about here is something that most economists have, for some reason that I don't quite understand, called energy theory of value. And it's a no-no in economics to talk about that. And I don't know why, but it's a no-no. Anyway, here's Robert Solow, who's one of the few most famous economists of the present day, who has insisted on these 3 points. He says, economic actors make choices based on 3 attributes. One of them is self-interest, call it greed. Second one is utility maximization, i.e. the idea that we actually calculate things. We calculate benefits and costs and make decisions on that basis. We all know that hardly anybody ever does that in reality, only maybe corporations do it, but most ordinary people don't do that. But that's still, yeah, his idea is that everybody does it whether they're saying it or not. And then finally, we have equilibrium. He says, the economy wants to be, he doesn't say wants, but I'll say wants to be in equilibrium and is always approaching equilibrium, is always close to equilibrium. And so neoclassical economics is basically all about equilibrium, near it, being near it. Far from equilibrium isn't there, it isn't in the textbooks. But our species, Homo sapiens, is not Homo economicus. We don't behave that way, you know. And Walras' law does not apply to living systems far from equilibrium. Walras' law, I won't go into now, you can look it up, it's quite easy to understand. It's basically saying that in a closed system, where everything in the system is made in the system and consumed in the system, then the prices have to add up to, you know, the money basically isn't really needed, or the price of, never mind, it's a simple law. So I could go, I think I'll have to skip this. It's too complicated. And here we come to the Schumpeterian wave. Here we're talking about, it's a little bit like Buzz Holling's law in ecosystems. Quite a bit like it. In Holling's case, you have some exploitation, then followed by crash of some kind, followed by some kind of recovery. And we all know that what Mr. Schumpeter said as a PhD thesis back in 1911, which has been finally translated into English in 1934. And he's now regarded as one of the great fathers of modern theory. And he's basically said that it's all about technology. That technologies are created somehow, and they run into limits, and somehow they get replaced by other ones, and that is what he called creative destruction. And so we have this cycle of creative destruction, followed by recovery, followed by a new period of that is supposed to explain the boom-bust system, the boom-bust cycle that I spoke about, that economists have been worrying about forever and have never, well, they now think that it's mostly Schumpeterian waves like this. And then the real question is, how do you explain that wave in economics? And that's where the problem is. In that slide that I skipped, which is mathematics, it shows Mr. Solo's first model explanation is, I don't know if it was thesis, PhD thesis, but right after it anyway. This was back in 1954, 56. The model says that we have something called a production function, which is a function of two variables, capital, labor. Because capital labor goes all the way back to the back in the 18th century. The French help me. I said it earlier. The French economists in the 18th century.
Yes.
Yes. Yes. They said that all production comes from agriculture, all wealth comes from agriculture, but the value of the wealth is increased by the amount of labor that goes into it. It's really that simple. And that simple idea with very slight modifications, I mean slight, that has continued in mainstream economics ever since. Wealth comes from capital and labor, human labor. Now, back then, muscles, animal muscles, did the work, a lot of it. Some came from wind, maybe a windmill or watermill, but a lot of the work was actually done by humans. And then you could call the animals a matter of capital. So you could say, well, humans did all the real work. Animals just were with humans said, okay, fine. That's capital labor. Now, Mr. Solo is trying to explain economic growth in the last 100 years, more or less. In this particular case, he was looking at 20, 30-year period, early part of the century, trying to explain economic growth in the GDP in terms of capital, stock. What's that? Well, it's whatever you invest every year and call it capital, and then it gets depreciated a little bit. And after a while, that's your capital stock. Depreciated summation of all the investments. And then the labor, what's that? Well, they count that for model terms, you would count it as employed personnel. Go to the Census Bureau. How many jobs are there? We talk about it every day now. Jobs, employment. So that's your measure of capital labor. How much could he explain? Well, there it is on your left hand. That's it. Right down the bottom. That's what he could explain using capital labor of the actual GDP. Roughly 1/8 of the total. And he himself confessed that having been rather shocked and surprised that so much of it didn't have anything to do with capital labor. Anyway, so this blue period section is what needs to be explained. We call it the solo residual, meaning the unexplained part of Solo's model. And here, just a bunch of graphs. I don't think you care much, but I will say, I'm just going to go to the end. Let's go straight to the end. There you see it.
This one.
Any one of them. These already explain how we could, by putting one more variable into the model, just adding one, but keeping the other two, the capital labor, adding one more, energy. Suddenly it's all explained. There it is. The one on that one there on the left, you see the red. I showed this one because it's most colorful. The red one I'm sorry, I didn't explain it right. What Solo himself did was to cheat. He decided, he knew he couldn't explain what I showed you. He cheated. He decided that this technological progress is happening. So he tried to reduce it, took a period of time, looked at the GDP at the beginning, GDP at the end. We have to explain that difference. And he said, okay, let's call it e to the k t, t is time. So what's the k that makes that exponential work? Then he does that. And he can find a k or a parameter that then goes into his model as an additional, as though it was something explained by economics, but it isn't explained by economics. It's just something you got from data. Okay, but that's what that red one is. We actually found that we could explain better than that by including energy as an additional variable. And that's what green and black is actual GDP and green is simple model. Now that's a simple model we had 15 years ago. In the last year, I think it is, we decided to get rid of the labor part altogether. We don't need it. So we redid the model without the labor, and we can explain it almost just as well. And I think that is probably a good place to say, okay, I appreciate your being so patient with me, and I'm sorry I'm not a very good speaker, but I find this stuff so fascinating. You can't drop it. So anybody has a question, you can take your.
Thank you, Rob. Please, if you have questions. Bob? No question.
No question. Okay,
You mentioned Ecology earlier.
yes.
How is that related to other sort of forms of energy, like enthalpy and Helmholtz free energy,
Okay.
thermodynamic?
Well, Helmholtz free energy is one version of Ecology for under certain circumstances involving pressure and so on. So I forget the details. It doesn't matter. Free energy in general would be Ecology. That's useful energy that you can do work while approaching it. That's Ecology. Do I need to say more, or is that no? Yes.
You were getting, maybe it's a technicality, but you were getting at marine organisms that might be able
Yes.
to recycle or consume or
Yes.
process
Recycle.
phosphate. Are you getting at diatoms, like marine
Anything that you know of that, I mean,
diatoms, I would say, because marine plant cells.
we actually have evidence though of
Well-
recycling in the ocean.
Yes, because first of all, these are largely photosynthesized, they're plant cells.
Sure.
So they're mostly famous for the silicon cycle, but those are the hard parts. But as plant cells, they're also consuming carbon, obviously, and nitrogen and phosphorus. And diatomaceous earth, which is fertilizer, I believe, is largely made up of compressed diatom, these marine plant cells. So I think what you're getting at is this kind of organism, like a diatom, that can do that. So I could be
Wow.
wrong, but I think that's,
I can't argue with you. I mean, you may
Yeah.
you may be right. You know, what I can say is that my understanding from the USGS people is that the phosphate rock, believe it or not, is almost all of our known sources of phosphorus in the Earth's crust, at least the part we're seeing, all came from some biological source first. That's the puzzle. And yet we know that most of the phosphates that go into the ocean end up on the silt at the bottom and then probably go down below. And that there's a long geological cycle and then it comes back up somewhere. But I need a faster cycle.
yeah. But I think diatoms are a big part of this.
Well, let's take a look at it.
Yeah.
Yeah.
Bob, two questions about this analysis. Do you measure labor and capital in monetary terms, like Solos did? Okay, and so if you manage to explain GDP with exergy added to those two factors, does it mean there's no role for technological progress anymore, or do you completely
Well,
substitute?
Marcus all got stuck into that exponent that Mr. Solo came up with.
Oh, I know, but therefore the Solos residual is called technological progress. That was the explanation, and that's where also endogenous growth theory came from, trying to explain the technological change over time. But if you match the real GDP so well, if you fit the curve so well, then exergy explains all that difference, right?
Yeah.
But how do you explain that if you look at the pattern of exergy over time, for instance, is there also a trend? Is exergy increasing
Okay,
faster than
I think-
labor or capital, for
I
instance?
think the answer that you're looking for is that the technology that has been changing over time, and it fluctuates. It is all in terms of it, you know, it's using exergy. That's why those ups and downs are explained. I think that's a simple answer.
But can you even separate exergy for the labor part and the capital part? Is that possible? Can you say how it's related to labor and capital? Because labor and capital
Yeah,
use the energy somehow, you know?
yeah, well, I think the answer to that is that the labor component in real terms is tiny.
Yeah.
I mean, the part that goes into jobs, human labor is tiny. We can do it, we can calculate it all in terms of food and so on, but it's really very, not in your, you know, Africa, there it might be much more significant. And it might be worth doing some analysis, you know, getting some data and calculating. But for the industrial world, where we live and where we have most of our data, the part that goes in the food is very small, actually. Einstein.
Yeah.
Keith, thanks for listening. Yeah.
Goes back to 69 to your article on material flows. One could probably analyze of this counting of the material flows by the people from Vienna and so on. So we know now that per year about 100 gigatons, a billion tons, comes into the economy and going on. So you could do the same kind of correlation between GDP and the material, the tonnage going into the economy.
I'm not catching all your words, I'm sorry.
I mean, I translate in English.
Speaking English is just,
No, I'm saying that if one goes back to 69 and you're,
no, I know the paper you made.
yes, and one would count the amount of materials coming into the economy. And then they become stocks and they go as throughput. Then one could do the same kind of correlation with GDP. Because counting the materials, this was not done before,
No.
but now
Right.
I am referring to Havel and the people in Vienna, and they have these accounts in just in tonnage. Of course, the tonnage is not
Yeah.
exergy, I
When
understand this.
you're talking about a project with a lot of data and, you know, a lot of graduate students.
No,
Well, a lot of students anyway, to do the work. I mean,
no, this has been done. I mean, counting the amount of tons of materials going into the economy. This is done, and in the last few years would be like
oh, sure,
100 billion tons per year coming.
sure.
If one takes this historically, one probably would find that the GDP
Oh,
is growing more or less like the tons in the economy.
okay.
A
All right.
large amount of the tons is
Right.
coal and oil and gas,
Yeah.
and also biomass and sand and gravel.
Yeah, we have good enough data on the material flows only for the last 50 years globally.
Yeah.
And yeah, we should go back. I agree.
But your point is that you can, instead of a KLE production function, you can do a CLEM production function,
Well,
right?
yeah, what is will be
And-
nonsense
And
because
materials.
the materials
Yeah,
are
the
very
materials are
diverse
very-
one from the other, but
So
I
it's
mean,
better fitting.
but this kind of regularity that the GDP does not depend on the capital and the labor, but depends on physical factors,
I hadn't thought about that.
applies to the exergy, I understand this, but also more simply applies to the amount of tonnage.
Maybe.
Yeah.
Talk about that.
Because the tonnage accumulates, which is different from
Sure.
all this is tonnage which has accumulated. And some of it becomes waste, as you explained in 69. But if you do the accounts, this could happen.
I'm talked out.
Thank you so much, everyone, for coming and joining us. And like I said, Bob will be with us for a few more days. So if you're interested in coming and chatting, he'd love
Yeah, I
to.
love to.